Let's start the second talk. So as our second speaker of the evening session, we have Professor Wei Li from the Institute of Theoretical Physics at the Chinese Academy of Sciences in Beijing. And she's going to talk to us about from BPS crystals to BPS algebra, constructions, representations, and applications. So please go ahead, Wei.
Okay, thank you very much for the introduction and for the invitation to speak here. I have 40 minutes, right?
But yeah, it's not that strict, but yes, for about 40 minutes, yes. Mm-hmm.
Okay, yeah, okay, thanks. So this is the title of my talk, from BPS crystals to BPS algebras, and I'll discuss its construction, representation, and some applications. So this is based on the following 3 papers with Masahito Yamazaki and Dmitry Galakov. So this is the first one that we studied how to construct this quiver BPS algebra as a quiver Yangian from the crystal melting, and this one generalized this. This one generalized to the toroidal and the elliptic case, and this one studies the representations. So let me first review the context of this this work. So this so the idea is actually very old. It's based on this Harvey Moore from last century. So they consider the BPS sector of 4D supersymmetric gauge theory, and they claim that it should have an algebraic structure. So the element of the algebra is the element of the is a BPS states, and the multiplication of this algebra is given by the fusion of 2 BPS states into a third BPS states. So this is supposed to be analog of the chiral algebra in the 2D superconformal field theory, and because it's the BPS sector, it should be robust, and it should reflect many, control many aspects of the theories. So Harvey Moore considered the perturbative part and also just a single particle states. So that's why they couldn't push it too far. So a major breakthrough was by Kenchevich-Soibelman in around 2010. So in the process of studying this wall crossing, they look at the entire BPS space, and then they found this BPS algebra should have this cohomological Hall algebra. So and meanwhile, this BPS algebra actually show up in many other phenomena, such as this BPS CFT correspondence, with this most prominent example being the AGT correspondence, which roughly says that the BPS observables in 4D n equal to gauge theory should take the form of some chiral correlators of 2D CFT. So in this sense, this BPS algebra manifests as a vortex operator algebra. And also in this beta gauge correspondence, where if you look at the vacuole in a 2D n equal to 2,2 supersymmetric gauge theory, the vacuole should obey some beta Ansatz equation. So in this sense, the BPS algebra will manifest as a Yangian algebra. Also in this corner VOA setup, so if you look at the supersymmetric Y junction in a 4D n equal to 4 super Yang and then you turn on some twist, then the operators that localize on this corner of this Y junction would furnish some VOA, and it's the truncated version of the VOA. And lastly, if you consider the intersection of the M2 and M5 in the twisted M theory, you will see an algebra called the alpha Yangian GL1. So all these different setups have one common feature is that they are all related to the string theory on some toric clubbable threefold. And although you see all these many different manifestations, actually they are all related. So the central player is this alpha Yangian GL1. So if you start from that, and you so this is known for the C3 case. So if you start from the alpha Yangian GL1 and you take the real subalgebra, you obtain this Koha. And also it's known that this is isomorphic to the universal enveloping algebra of the W1 plus infinity. So roughly speaking, if you do a change of basis, this alpha Yangian GL1 is the same as this vortex operator algebra. And then we'll do the truncation. This will be the algebra that show up in this AGT or this corner VOA story. And finally, from this Yangian formulation, you can obtain this beta Ansatz equation. So the status of this story is that so before our studies that this is more or less known for the toric-Calabi-Yau threefold without the compact fourth cycle. So so let's focus on this one because this is the central one in this web. So for these special cases, the BPS algebra will be the alpha Yangian of some superly algebra. It's either GL/n or this D to 1 alpha. So correspondingly, that will correspond to some Lie algebra extended W algebra. So my goal today is to explain that how we generalize this whole story to include the all toric-Calabi-Yau threefolds. So because you see this web, so I mean we could have choose any of this formulation, but you see this one is the central one. So we want to choose this type of algebra as the focus. So because it's so we want to determine the Yangian version of the BPS algebra. So this because it's Yangian, so we need to extend this original definition. So originally they only considered this multiplication, so which correspond to the fusion of the BPS states. So if you want to look at the Yangian version, that means that you also have to consider the co-product. So roughly speaking, correspond to the decaying process of one BPS states into two BPS states. So after you've got this, then you can translate to other realizations such as the VOA or Koha or R matrix, and then you can directly check from other setups. So the setup today is that we consider the type 2A in a general toric-Calabi-Yau threefold, and we look at this half BPS states, which are given by the D-brane wrapping holomorphic cycles of this threefold. So we look at the effective description of this BPS sector. So this is given by a equal 4 quiver quantum mechanics. So then we're going to use the fact that the BPS states have a description in terms of some colored 3D crystals. And then our BPS algebra would act on this. So the main point of construction is that under some Ansatz, we can start from this the set of crystals, and just based on the fact that this BPS algebra has some nice action on this, we can bootstrap the algebra itself. So in the end, that means that starting from the toric data, we translate this into the quiver data, and then use this as input. So once we know how to do this, we can actually bypass this middle step. So there's a prescription that's like half page long that once I tell you this quiver data, you can immediately write down this quiver Yangian. So this has actually many advantages relative to other approaches. So one is that you can very easily write down the explicit algebraic relations. And this also applies to all the toric color threefold in one go. Also, this is very easy to generalize to trigonometric or elliptic versions. And also, it's very easy to describe all the representations. So after I explain how to get algebra, then I'll show you how to describe the representations. So the representations in this framework will be given by the subcrystals, and they will describe all the other chambers and also include the open BPS counting. And this can be translated into the framing of the quiver. Okay, so here's the plan. So I just finished the introduction. So I'll first explain what this is a BPS crystal, and then I'll show how to bootstrap this BPS algebra from the crystal, and then I'll discuss the representation and summarize. So this is the setup. So we look at the type 2A string and toric labial threefold. So this is the easiest one, the C3. And then the remaining one, roughly speaking, has two types. One is those without the compact four cycle that correspond to the toric diagram without the closed loops. Or so the difficult ones are those that with compact four cycle. So those are with some closed loops in the toric diagram. So, but in our construction, they're all we can treat them in the same way. So this give you some 40 into 2 gauge theory, and then we put some branes and look at this for half BPS sector. So that would be some D-branes wrapping some holomorphic cycles. So we look at those days with 1 D6 and then some D2 and D0. So at the first step, we wouldn't have any D4, and so they actually correspond to the truncations of the algebra. So now the question is, what is the BPS algebra underlying this BPS sector? So now we have to first describe this BPS states. So the low energy effective theory of this on this bound states is given by this intuitive force quiver quantum mechanics. So the quiver data has this the set of vertices which correspond to the gauge group, and the set of errors between vertices, so which correspond to the bifundamental, and then some superpotential. So the data is the quiver and superpotential data. So we can repackage this quiver and superpotential data into a periodic quiver, such that so this periodic quiver is just a you try. So this is a C3 example has which has one vertex and 3 adjoint here, and this is the superpotential. So the periodic quiver is just that you try to draw this on a T2. So this is a drawing on the, I mean, this is supposed to cover the entire R2, but I'm only drawing this this bit, and this is the fundamental domain. And so this periodic, so the correspondence to the quiver and superpotential is that inside your fundamental domain, each phase corresponds to a term in your superpotential, and the orientation along this of the arrow along this phase correspond to the signs of this monomial terms inside your superpotential. So why do we want to do this? So so this is because we'll go back to the state that we want to consider. So each D-brane bound state with some charges, this will correspond to some T2 invariant states of the quiver quantum mechanics with some rank, and which in turn correspond to a module of the path algebra of the Q mod F-term constraint, which correspond come from the superpotential, and this is given by a 3D molten crystal configuration. So I'll start explain what is a molten crystal mean, and with this number of with some number of atoms. So the way to obtain this set of molten crystals is that you take this periodic quiver and then you do an uplift, and then you obtain some infinite 3D crystal, and from there you can melt, and so you get some finite pieces of molten crystal. And then this the generating function of this crystal would reproduce your BPS splitting function. So let me try to explain this with some examples. So we already see the C3 example. So this is the quiver and the superpotential, and this is the periodic quiver. So remember, this periodic quiver is infinite, and I'm just drawing this small bit. And so now you have to choose So you have to choose one point as your origin, and starting from that origin, you do an uplift. So you obtain this. So also I'm only drawing a small part. So this one should be infinite. So this is the origin, and this is the x1, x3, x2, x3 direction. So this is supposed to be a infinitely large crystal, with this being the origin. So yeah, you can just stop me and ask. I'm not sure whether this is clear enough. So once you obtain this full crystal, and you start from this origin, and then you can melt this crystal. So so the part that you remove from this origin, that will correspond to this finite bit. That's called molten crystal. So if you don't take anything away, so this will correspond to the so these two pictures are equivalent. So except that it's easier to consider these finite bits than this infinite part. So this is the vacuum, and this will be the. So if you remove one atom here, this will be the one atom excited states. And for this one, this example that I removed 4 atom. So there's certain ways to remove the 4 atom. So if you do this, you can check that this reproduce the magma function, which is the BPS counting for the C3 case. So you can repeat this for arbitrary Clavier. So for example, this is the conical case. This is the periodic quiver, and then if you do the uplift, you get this famous pyramid. And this is supposed to be infinite large, and this is the tip. This is the origin of the pyramid, and then from here you can melt. So you can melt first one white atom, and then one white and one white, one black. So there are 2 choices, and then the next one you have 4 choices, and this one has 1 choices. You can see that this reproduce the BPS counting here. Up to some sign. So this is some other example. This is the C2 mod Z2 cos C. This is the periodic quiver, and this is the C3 mod Z3. So because these two are both orbifold, so you see that it doesn't change the shape relative to the plane partition case. It just adds some color. So this is you're doing orbifolding on this on two of the 3 directions. So that means that you're oscillating on this x1 and x2 directions. So the color is changing, alternating blue red on these 2 directions. And then on the 3rd direction, you're not doing any orbifolding. So it's constant. The color is constant. So for this one, so you're doing the orbifolding on all 3 directions. So the color is changing on all 3 directions here. So so now let me focus on this one here. So this is an infinite crystal. So I want to consider the molten crystal that's you melt from this infinite crystal. So meaning that so I start from this tip, and then I just remove some finite number of atoms and consider those configuration. So this is actually, I'm flipping this because I want to draw this as a two-colored plane partition. So now let me quickly explain how do I grow this BPX crystal from a periodic quiver. So this is a periodic quiver. It should be infinite, but I'm just drawing this finite bit. So first I choose origin. So let's choose here, and then so each pass from your origin corresponds to a particular atom. So the first atom will just correspond to this origin to itself, and then the origin from next one. So this pass corresponds to this this red atom, and then this pass with two arrows that correspond to the third atom. So for each atom, so look at this atom, this blue atom, it can have different paths that reach here. So we need a notion of the equivalence of paths. And so as I mentioned earlier, so the molten crystal we considered is not just any bunch of atom. It has to be the configuration that you obtain by removing atom one by one, starting from the tip of your crystal. So that means that there's some rules here. I mean, what kind of configuration is allowed? So this, I mean, you can just picture that. I mean, you can either picture this crystal configuration as something that you can remove one by one from this infinite or your original infinite crystal, or I mean, you can just check that. So this rule says that each atom has some precursor that has some arrow pointing to it. So all the atoms, the precursor have to be already inside your crystal before you can add this crystal. So in the complement language, that means that you have to you have to remove the atom that closer to the surface before you can remove those that's more inside your crystal. So for example, this is allowed configuration because if you focus, for example, focus on this blue one. So this one has a one precursor, which is the red one that points to it. So this is already there. So that means you can also add this one. But this one is not allowed because this blue one has two precursor, which is this two. But only one of you only put one of them in your crystal. So another way to see is that you should think of this as a two-color plane partition. So this obviously is not a plane partition configuration. So if you want to add this blue one, you have to add both of this red one first. So and then so you just do this as you, and then when you add all this, when you go along this quivers, you have some closed loops. So each time you have a closed loop, you go deeper inside your crystal. So for example, this is your original one. So this is all the crystal that I have added. So you see that I haven't had any closed loop yet. So now suppose I start from this one and then I go back. So now I have one closed loop. So this one, the new one, will have a depth one. So this is all the old story of crystal melting story. So the new ingredients that to derive this BPS algebra, we want to consider the toric fixed point. So we want to put the whole thing in the we want to turn on the omega background. So which means that we should assign some equivariant weight to everything. So we want to assign, so for each atom, it should have some weight. So from this definition that the atom corresponds to a path, So that means that we first assign a weight to each arrow, and then the weight of the atom corresponds to the sum of all the weight of the arrow on this path. And this equivalence of the path just translate into the loop constraint. So meaning that if you go around a loop, the sum of all the weight should sum up to be 0. And so when you project this 3D crystal back to the periodic quiver, so this if you project to the same vertices, so then they will correspond to the different atoms with the same weight. So now we see. Let's check that we have the this is right prescription, so we can check that how many independent equivariant parameters we have. So so to start with, we assign one weight for each arrow. So we have in the beginning there the number of the weight is equal to the number of the arrows, and then we impose this loop constraint, so that so then we have the constraints number of faces -1, and so this corresponds to the global symmetry, and we can also impose the gauge symmetry. So this is give us the number of vertices -1. So after we include both the loop constraint and vertex constraint, we can check that this number of parameters is precisely 2. So which is the number of the equivariant parameters for this toric labial omega background. So now we understand what is PPS crystal. So now let's see how to bootstrap the algebra from it. So so the trick is that so originally we say we want to study the fusion of arbitrary 2 PPS states into a third PPS state. So the trick is that we focus on some process in which one of them is a unit PPS state, which is given by this one atom. I mean, it's not just. I mean, this is not just one. I mean, it should be for if you have like more than one color in your crystal. I mean, there should be the however many colors that you have. So you can have say you have 2 colors, then you should have 2 different types of unit PPS states. So for each atom, we have a family of generators. So I have a raising. So for each color, I have a raising and a lowering operator, and also a cation, and which have its own mode expansions. So to fix this algebraic relation, we need to first fix this action on the set of all the this PPS crystal first. So first we write down some ansatz. So this ansatz is inspired by this the C3 case. The C3 is the alpha Yangian GL1. So that has a nice action on the set of plane partition. So this is a generalization of that. So the ansatz is that we want this the set of crystal that we constructed earlier to be the eigenvalue of all the 0 mode. And the point is that this eigenfunction is very easy to write down. So it factorizes into a product of just many contributions. So it's so vacuum has 1 contribution, and then each atom in your crystal has a contribution. So this is the color A. This is the cation for the color A, and then all the atoms will contribute to this. It doesn't have to be the same color. So then they have this relative bounding factor. So it should be the ansatz is that it's the same function, and with some shift of the coordinate given by the weight of the atom. And then the E operator. So you start from any crystal configuration. So what the E generator does is that you add an atom in all the possible places, and then the F generator would remove all the atom in all the possible places, and then this coefficient is completely controlled by this the eigen function of this this crystal. So this is one example. So so if I consider this two crystal states, so this is the initial state. So if I apply this E, so there, I mean, I can apply both E1 and E2. So then it has three possible final states. So there's this three possible places that you can add the next atom, and then or I can. So this is the removing the result of the removing process. So starting from this, I can remove this red one to obtain this final one. So this is the ansatz. But I haven't told you how to fix this this most important ingredient, this relative binding factor here. So so to fix this, so we have two requirements. So one is that we want all this to be automatic. So which means that all this we don't want to. We know what we want to do. We want to apply this to arbitrary crystal, and we want to generalize all the possible final states. So we want, so that means we want all this to happen automatically. So that means that all the poles of this eigen function has to have the meaning. Either correspond to a place where you can add atom, or you correspond to a place where you can remove an atom. And we want this melting rule that I explained earlier to be automatically satisfied. So it turned out that this is the result. So so for the relative binding factor from color B to color A, so you have some factors in the denominator and the numerator. So the denominator is all the arrows from B to A, and then the numerator is for each arrow from back to A to B give a factor. I think I'm running out of time, so I think I'll skip this example here. So this example just tells you how you can do this step by step. So everything is just automatic. So for example, this level 2 case, you start from a particular configuration, and then you write down these two charge functions, and then you look at its poles. So that tells you where you can add the atom and where you can remove. And then you can check that this melting rule satisfied automatically. So now I have this. Now I have fixed this action, including all the details. So now what should I do to obtain the algebra itself? So then I just apply and so this is just applying it once. So now I just take any two operators, I apply twice. And then I reverse the order, and then I compare the two. So then I immediately write down this the algebra. You see this bounding factor which just appears here, and then there's some statistic factors. And then so this is look like OPE of the 2D CFT. So with this mode expansion, I can plug in the mode expansion, and then convert it into a relation with the modes. So here you see a difference between the case without the compact first cycle and the case with the compact first cycle. So the difference is that when you don't have a compact first cycle, your quiver non-chiral. So that corresponds to this binding factor being homogeneous. And for the more difficult case, you have chiral quiver, and then this all can be inhomogeneous. So that will change this how this zero modes are expanded. So then you can immediately translate into this algebra in terms of mode, and then you can compare to the non-algebras. For example, for the for this class of toric labial, we can check that this is known. reproduces alpha Yangian some super Lie algebra. And for the general Torre-Clavier, our algebra is new. And so this formulation or this basis also make it very easy to generalize to trigonometric and elliptic case. So in this binding factor, you can just remove this rational function by some ratio of a sinh function, and then you get a toroidal algebras, or you can remove it by you can replace it by some ratio of some elliptic some theta functions. So this is the elliptic version. This is the you obtain the corresponding elliptic quiver algebras. So, and then you can also confirm this. So this rational case corresponds to the quantum mechanics. So, and this trick case corresponds to the 2D 2,2 gauge theory, and then elliptic case corresponds to the 3D n equal to 2 theory. So Rak, I have how long? I have 3 minutes.
Yeah, 6 minutes. 6 minutes. About 6 minutes.
Okay, so let me just explain the main point of this representation. So everything I said before. So this crystal, you see so they all have the same feature, that the starting point is just one particular has just one item. So you have one item in the tip that's what you can add in your first step. So that corresponds to that this quiver is canonically framed. This chart function has this this simplest form. But we know that this crystal just corresponds to one particular chamber, which is the non-commutative DT chamber, and it only has a closed PPS, only correspond to a closed PPS invariant. And we know that there are also other crystals that we can consider, such as this other chambers, where you can also include this include open PPS states. So so it turns out that this language actually allows us to consider the arbitrary subcrystals. So so we can describe arbitrary subcrystals as a superposition of positive or negative canonical crystals. So and then we can translate this into the non-vacuum representation of this the same algebra, and then we can translate this into the framing of the of the original quiver. Let me just, for example, if you look at this particular shape, I mean, this is just a 2D simplification of the 2D projection. So you can see that I can obtain this one by having two positive crystal and then one negative crystal here. And then this is some more complicated stuff. So this is an example of the conical case. So in starting from the original one, I can crystal. I can build this crystal by superimposing 3 positive crystal and 2 negative crystal with some precision here. And so once I know the set of positive and negative crystal, and with this their positions, I can translate this into this the contribution of the ground state to your chart function. So you see that it only changes this ground state. So that means that just from this information, I can immediately define this some non-vacuum representation that correspond to this particular subcrystal. And the position of this positive and negative crystal, and also tells you how to translate this into the framing of the same quiver. Okay, so let me summarize, and you can ask me for the detail that I skipped later. So what we have done is that we consider a type 2A on a generic Torre-Clavier threefold, and we look at this PPS sectors, and then we use the description of the 3D molten crystal description of the BPS states, and then from there we can bootstrap this BPS algebra as quiver Yangian. So the main result is that once I give you this quiver data, you can immediately write down this quiver Yangian. Like this, it's just half a page here. So the information from the quiver comes in as this bounding factor, and then this statistic factor here. And the advantage is that you see this is very explicit. And this procedure applies to all the Torrey-Clavier threefold. And as I mentioned, you can easily generalize to trigonometric and the elliptic versions. And also, we can easily describe non-vacuum representations. So I skip this. So some future directions. So you see, we can actually describe pretty arbitrary subcrystal representations, but most of them we don't know what are the D-brane descriptions. So then it gives the natural questions: what are the BPS counting problems that this correspond to? And also, I only explained this quiver Yangian version of the BPS algebra. But as I mentioned earlier, it can have many other manifestations in other setup, in other kind of problems. So we can try to translate our Yangian algebra into other formulations and then apply to other problems, such as this R matrix, which would give us more beta gauge correspondence, or this VOA, which give us more BPS CFT correspondence, or also the truncation might hopefully give you even new rational CFTs. So more ambitious, maybe we can generalize to Torrey-Clavier fourfold, or even beyond. Yeah. Okay. Thank you. Let me end here. And
thank you very much for the very interesting talk, Wei.